Hello again, this is Dr. Olson for Meteorology 2010 at Daytona State College. This is the second video for Chapter 1 on the Earth's atmosphere from the textbook Essentials of Meteorology by Dr. Ahrens. In this video, we are going to move on to talking about the structure of the Earth's atmosphere and what the atmosphere looks like in a perspective of pressure and temperature. So a lot of the weather that we experience from day to day depends on the properties of the atmosphere for that given day. So that is what we're going to be looking at in this video. But before we can actually see some of these properties of the atmosphere, we need a few mathematical definitions. Now, I will say this, there is not much math involved in the course, in fact, very, very little. There will be some in Chapter 4, a little bit in Chapter 3, but that's pretty much it. In fact, here all we're doing is looking at definitions. You don't need to worry about future calculations, just understanding what it is. So the first definition we need is density. And density is how much mass or matter is in a given volume. So you would calculate it by taking the amount of mass, divide that by the volume. So let's say we have 15 kilograms of some sort of a liquid, and that is in a volume of 3 cubic meters. Then the density would be the mass, 15 kilograms, divided by the volume, 3 cubic meters. So we have a density of 5 kilograms per cubic meter. Excuse me. So that is density. Basically just how much stuff is in a certain amount of volume. That's pretty much what density is talking about. The second definition is weight. Weight is different from mass. We often confuse them and treat them as the same, but they are fundamentally different. Mass is how much matter you're made of, and weight is how hard gravity pulls on that mass. So to calculate weight, we take the mass of the object and multiply that by the acceleration of gravity. So if we take our liquid of 15 kilograms, then its weight would be the mass, 15 kilograms, times gravity, which is about 10 meters per second, giving you 150 newtons. You don't need to worry about that unit. That's a physical number. Just know that 150 newtons is roughly about 33.7 pounds. So that is weight. Weight is how gravity affects a mass. Third definition is pressure. This is one of the more important definitions. Pressure is defined as force per area. In other words, it is what is felt as a certain force is applied over a certain area. For meteorology, we're more concerned about the weight of the atmosphere, so we just change that force to weight per area. Just as a quick illustration of pressure, imagine yourself standing on 1 foot. Your 1 foot starts to hurt pretty quickly because your entire weight is distributed over the smaller area of just 1 foot. Whereas if you stand on 2 feet, you've increased the area, your weight is distributed over more area, decreases the pressure on your feet, you can stand for a whole lot longer because the pressure doesn't hurt as much. Just an illustration of this calculation of pressure. So if we take our liquid of 15 kilograms, which we saw has a weight of 150 newtons, 33 pounds, and let's say that that weight is distributed over an area of 2 cubic meters, then the pressure would be weight over area, 150 divided by 2, or 75 pascals. Now the pascal is a base unit for pressure, and the unit that we will be using most often is based on this unit of Pascal. But that is equivalent to about 0.011 pounds per square inch, or PSI. Now, everyone here in America has seen PSI. That is exactly what PSI is. It's a unit of pressure, pounds, or force, per square inch, or area. All right. So, as I said, the pressure variable is one of the most important ones in meteorology. So let's take a quicker look. Um, the atmosphere is made of compounds and chemicals and other elements that have mass, and so they also have weight at the surface. And because there's weight to the atmosphere, we're going to feel a certain amount of pressure due to the weight pushing down on us. What is that pressure? Um, Common numbers, 101,325 pascals. That's the basic unit that we saw on the last slide. Divide that by 100, you get 1,013.25 millibars. This is the most common unit that we will be using throughout the course, is millibars. That also equates to about 14.7 pounds per square inch, or 29.92 inches of mercury. That comes from the barometer that you see here on the right. If you have a complete vacuum in the top of a tube and put that vacuum in a cup of mercury, atmospheric pressure would push the mercury 29.92 inches up the tube. That's a typical standard atmosphere. Or we could just simplify it all the more and just say 1 atmosphere. So what does the pressure look like in our atmosphere? The air in our atmosphere is most concentrated close to the ground, and as you get further and further up, there are fewer and fewer molecules. So another way of saying this is there's a lot of mass in a given volume here. In other words, it has a high density. Then as you go higher in the atmosphere, you have fewer molecules per unit volume, so it's a lower density. So this orange line indicates what the density would be. It just gradually decreases as you get higher and higher and higher in the atmosphere. Now, what would the pressure be? Well, at the surface, you're experiencing the pressure of the entire atmosphere. So this is where you're going to have the highest pressure. But if you go up, then you're only going to feel the weight of what's above you. So, since you go higher in the atmosphere, more of the atmosphere is below you, that means the air pressure is going to be decreasing with height. So air pressure also has a very similar line as air density does. Okay, so what does this look like for our atmosphere? Here's a great look at what it might look like in our atmosphere. Here at the surface, we have a pressure of about 1,000 millibars. Remember the last slide, 1,013.25 millibars. Right there. That's one standard atmosphere. We often round that to just 1,000 millibars just for estimating. So at the surface, it's about 1,000 millibars. Half of that would be 500 millibars. So at this height of roughly 3 or 4 miles, you have a pressure of 500 millibars. That means you're on top of half of the atmosphere at this height. If you go a little bit higher, 300 millibars, that means you're on top of 700 millibars, or 70% of the atmosphere. That's what it would be at the top of Mount Everest. That's why we need oxygen tanks whenever people climb Mount Everest, is because there's not much air up there. The density is much, much lower. And if you get to about 9 miles, then you'll be above 90% of the atmosphere. And then up to about 18 or 19 miles, you're above 99% of the atmosphere, and so on. It continues to have an exponential type of decrease. All right, that's what the pressure looks like. Now let's take a look at temperature. How does the temperature change in the atmosphere? Normally, the temperature decreases with height. In other words, if you hopped in a weather balloon or hot air balloon and start rising, you would feel the temperature start to drop the higher you are. The lapse rate is how quickly the temperature changes with height. On average, the atmosphere cools at a rate of 6.5 degrees Celsius per kilometer In English units, that means about 3.5 degrees Fahrenheit per 1,000 feet. So if you were to hike up a mountain, it's 46 degrees Fahrenheit at the surface. Every 1,000 feet, the temperature should drop on average by about 3.5 degrees Fahrenheit. That's what the atmosphere looks like on average. However, it's not always that way. There are variations. You can have what's called an isothermal layer. An isothermal layer is a layer of air where there is no change in temperature with height. In other words, you hop in your hot air balloon, you measure the temperature at 50 degrees Fahrenheit, you go up, it's still 50 degrees Fahrenheit, there is no change. You also have an inversion, which is where the temperature actually increases with height, instead of the usual decrease with height. So now we're ready to talk about the layers of the atmosphere. Here's what the atmosphere looks like. The bottom layer is called the troposphere, where the temperature decreases with height. At about 11 kilometers, that's about 8 miles up, that stops, and we end up having a small isothermal layer called the tropopause. Everywhere from the surface to the tropopause, that's where our usual weather takes place. So this is where our course will focus for the most part. It's down in this troposphere. Above the tropopause, we actually have an inversion layer. We have an inversion layer where the temperature increases with height. This is because there's a large amount of ozone in the atmosphere, absorbing high-energy radiation, protecting us from that high-energy radiation. Because it's absorbing that energy, it increases in temperature, warms up, and you have an inversion layer. At the top of that, you have the stratopause, another isothermal layer, where it starts to switch and temperature starts to decrease with height again. This is called the mesosphere. Above the mesosphere, you have the mesopause, and above that, you're pretty much out in space, exposed to direct sunlight, where the temperature can increase quite high. And this is called the thermosphere. The thermosphere extends quite a ways out in space. When the sun is on an average cycle, you could expect a temperature like this orange line. But if the sun is really active, temperatures in the thermosphere can increase quite a bit, almost double or triple even. Now, a lot of people are taught that the International Space Station is really out in space. Technically, it's not. This blue line indicates where the International Space Station flies. It's still inside of our thermosphere. It's just that the density is so low that it practically is space up there. But it is technically still part of our atmosphere. Now, let me come back here. Up through part of the mesosphere, we pretty much have a normal atmosphere, but something interesting happens with the mesosphere. Upwards, the sun is so active that a lot of the compounds ionize. In other words, they become either positively or negatively charged as electrons are added or stripped off of atoms. That region is called the ionosphere. That's this blue line over here. So we'll talk about the ionosphere, which is an electrified region of the upper atmosphere, as we just explained, due to absorption of solar radiation. There are three regions. The lowest region is the D region, the middle is the E region, and the top is the F region. Now, the difference between these three is that at night, the D region disappears because all those charged ions recombine, and then you don't have any ions anymore. The E region is much stronger and only partially disappears, does not disappear completely at night. And the F region, it doesn't disappear much at all. It's there day and night. Well, woohoo, what does the ionosphere do? Well, a lot of things. Here's one thing. It affects radio communication. When you have a heavy ionosphere, then it can block communication, but when the ionosphere is weak, communications, like at nighttime, communications can travel quite a ways.